Yeah, so there's also another problem here that I want to show whether the given transformation is one-to-one or onto. So determine whether T such that R2 maps to R3 defined by take a two-dimensional vector and then it will transform to give us a three-dimensional vector. Is whether this is one-to-one or onto. Okay. Again, in our previous lesson, I said that T is one-to-one. It depends on what you've learned or what you've been introduced to, if and only if the null space of T is equal to the zero vector. Okay. I'll prove the other way as well, that that uses the normal definition of one-to-one. Okay. Then what do we mean here? It means T of a1 a2 should give us 0 sorry, zero vector in the three-dimensional space, because that's the range, right? The null space is all the transformation, all the vectors that when you transform them you get the zero vector in the codomain or in the range. Okay, so here T of a1 a2 is equal to 0 0. What does it mean? It means that if I transform this, I should get 0 0, right? When I transform that, the one on my left, the transformation is given by a1 plus a2, 0, 2a1 minus a2 should be equal to 0 0, right? 0 0 0. And here two vectors are equal. It means that a1 plus a2 should be equal to 0. And here the other part, the middle is consistent, right? 0 is equal to 0. It makes sense. And 2a1 minus a2 should be equal to 0. Now if I add these two equations, if I add them, let's call this equation 1, let's call this 2. If you add equation 1 and 2, you're going to have 3a1 should be equal to 0. That means what? A1 is equal to what? 0. Right? If a1 is equal to 0 from equation 1, 0 plus a2 should be equal to 0. So a2 should be equal to 0. So it means that the only vector that transforms to give us 0, a1 equals 0, a2 equals 0. So it means the transformation of the 0 vector is the only thing that gives us 0. So indeed, the null space of T is just a 0 vector. So T is what? T is one-to-one. On the other hand, you could also use the definition of just one-to-one, that T is one-to-one if and only if T is one-to-one. Let me just use this definition. Then T of x, a vector x, is equal to T of y, imply that x is equal to y. Right. So if you can, if we assume that a vector or the transformation of this vector x equals a transformation of another vector y, that could only happen if x and y are the same. If we can show that, that means T is one-to-one, right? So that this approach doesn't use any theorem that you know, it uses the definition of one-to-one. Okay, so let's name or let's define the vector x to be a1 a2, and then define the vector y to be equal to b1 b2. Okay, now what is T of x1, or T of x is equal to if you go back to the transformation, it's a1 plus a2, that's the first vector plus the second vector. So this is T of a1 a2, and it's equal to a1 plus a2 0, 2a1 minus a2, and T of y is equal to T of b1 b2, and that is b1 plus b2 0, 2b1 minus b2. Right, and we are saying if the transformation, we are saying that the transformations are the same, right? So suppose T of x is equal to T of y. What does it mean? It means that a1 plus a2 0, 2a1 minus a2 is equal to b1 plus b2 0, 2b1 minus b2. Now these transformations are equal, then x and y should be equal. What it means for x and y to be equal is that we should make sure that a1 is equal to b1 and then a2 is equal to b2. That's what we are looking for. Okay, from the first component, a1 plus a2 is equal to b1 plus b2, and the middle component is consistent because you have 0 equals 0. That is okay. And 2a1 minus a2 should be equal to 2b1 minus b2. Now let's add these two equations. If we add equation 1 and equation 2, if you add them, what does it give you? It's going to give us that 3a1, because if I add these two, I'm going to get 0. Alright, so 3a1 is equal to 3b1. If I divide through by 3, I'm going to have a1 to be equal to b1. Alright, if a1 is equal to b1, now let me go to equation 1. What will happen? I'm going to have b1 plus a2 is equal to b1 plus b2. Now if I send b1 to this side, it's going to be minus, and I'm going to have b1 minus b1, that is 0, so I have a2 equals b2. Right, so that's what we're after. We've been able to show that a1 equals b1 and a2 is equal to b2. So it means the vector x is equal to the vector y if that their transformations are the same. And that concludes the fact that so t is 1 to 1. Right. Now the other part that we are supposed to show is that is t onto or not. Okay. Now the transformation t is defined to be t of a1 comma a2. That is a two-dimensional vector gives us a1 plus a2 0 2a1 minus a2, right? So that's the definition of this transformation. Now to show that this is a three-dimensional vector space, this range here, we should show that the range of t, which is given in this form, right, is given to be a1 plus a2 0 2a1 minus a2. I define it like this because that's the product, that's the output we want, and that is the range of t. We know this belongs to this value that we have, or this vector will always belong to R3, right? If you go by that, the definition of the t is R2 to R3, so the whole of R3 is our codomain. If we can show that the whole codomain R3 is the same as a range, then t is onto. Now, since any element you can pick in R of t will belong to R3, means R of t is a subset of R3. The other part to show that will conclude that R of t is actually equal to R3, or want to show this R of t being equal to R3. The other part to show is that if we can show that R3 is also a subset of R of t, then we are done, right? But let's look at this vector. All the vectors in the range of t has 0, or they have 0 at the middle, right? But it's not every vector that you have in R3 that has a 0 at the middle, or as the middle value. If I pick the vector, say 0 1 2, this will never belong to R of t, because R of t is defined in such a way that always the middle is 0, right? So it means R of t is not equal to R3, because this vector I'm talking about here, 0 1 2, belong to R3, but that same vector does not belong to R of t. So it means R of t is not equal to R3, because there are other vectors in R3 that are not in R of t, so these two sets are not the same, meaning that t is not onto. Alright, so that is how you show these two things, onto and one to one. Right, see you in our next lesson. Okay.